Hello everyone, I hope you're all doing well. We will be looking at Cartesian 3D vectors, and we will be defining something called as a coordinate and direction angles during this concept talk. Okay, let us first start off by drawing the Cartesian 3D axis, the Cartesian 3D coordinate system. Okay, so Cartesian 3D coordinate system. Alright, and here is how we typically define the Cartesian 3D system. First of all, let me draw it out, and then I can show you how we get it. Okay, so I'm going to draw three axes. All of them are mutually perpendicular to each other. And I'm going to label this axis as the x-axis. I'm going to label this axis as the y-axis. This axis is going to be my z-axis, and each of them are at right angles to each other, okay, or mutually perpendicular to each other. Okay, so how do we get this system of axes? So first of all, these are three axes: the x, the y, and the z axes are mutually perpendicular to each other. All right. So one quick way of obtaining this axis is as follows. It is a little hard to visualize this because I'm not doing this in person, but here goes. If you take your right hand, okay, and then you align the arm along the y-axis, the direction of your thumb along the z-axis, then the direction of the curl of your fingers will be along the x-axis. Okay, and this is called as a right hand rule, and I'm going to write it out. Okay, so right hand rule or right-handed axis system, what you do is the following. Okay, so you take your right hand, and then the second step is align the direction of your arm along the y-axis. Okay, third step is point your thumb along the z-axis, then the direction of the curl of your fingers of your right hand, your right hand fingers will point along the x-axis, and you can pretty much follow this procedure for you can align your arm along the x-axis and then your thumb along the y-axis. The z-axis will be given by the direction of the curl of your right hand fingers. Okay, so this is typically the right hand rule. It takes a little bit of practice, but you'll get used to it as we draw it off and on. All right, now I want to draw a vector, a force vector on this coordinate frame. Okay, so here is the force vector that I'm going to be drawing. So starting from here, let me maybe draw a force vector up to there. Okay, so this vector is the force vector F. And since we are in the Cartesian coordinate system, the components are the same as the projections. Okay, so here also the components are the same as the projections. Okay, And before I go ahead and do all these axes, I'm going to write out the unit vectors along the x, y, and the z. So along the y-axis, the unit vector, as you know from before, is j along the positive y. Along the positive x-axis, I'm going to call the unit vector as your good friend little I. Okay, this is from before. And then the unit vector along the z-axis will be given by the letter k. Okay, so I, j, and k are the unit vectors along the x, y, and the z directions. Okay, so I, j, and k. These are unit vectors along the positive x, positive y, positive z axes. All right. So once I do these, how do I find the components of the force F? Here is what I do. Okay, from the head of the force F, I drop projections onto the xy plane first of all. Okay, so I drop a projection onto the xy plane, and then I drop a projection onto the z direction. Okay, and I'm going to copy that and paste it here so that I can join this line here. Yes, in a sense, and you can see that I'm getting some kind of a rectangle here, and that is because this angle here is 90 degrees. Okay, likewise this angle here is also 90 degrees. And then here is also what I do. I take the projections and then on the xy plane, and then I project it onto the y-axis, and I project it onto the x-axis, and this is going to be 90 degrees here. This is going to be 90 degrees as well. And how do I get the projections? From the tail of the force vector F all the way to the point of intersection is how I get the projections. Starting from here all the way down to there, point of intersection, I get another projection. Starting from here all the way up to there, I get the third component, okay, or to the point of intersection there. So this is going to be vector F along the x-axis. This is vector F along the z-axis. And then this guy here is going to be vector F along the y-axis. Once you have these components, then it is fairly straightforward to write the vector itself, okay, which is what I'm going to be doing. Vector F is the vector sum of its components, okay. So vector F is the vector sum of its components, fx, fy, and then fz. But then we know that the fx vector is along the I direction, fy is along the j, and fz is along the k, which means that I can take each of them and write them in terms of their unit vectors I, j, and k. Okay, so that's typically what I'm going to be doing. Okay, so this means that the force vector F can be written as fx times I, fy times j, fz times k. Okay, and if I need to find the magnitude of the force vector, then I can also, so this is called the Cartesian form. Okay, let me write that down here. So this is the Cartesian form of vector F. Then if I want to find the magnitude, I can do the following. Okay, magnitude of F is going to be fx square magnitude, fy square magnitude, fz square magnitude, square root of that. Okay, and this is going to be the magnitude of vector F. Magnitude of vector F. All right. So now one more thing that I'm going to be defining here on the same figure as we go up are three angles. Okay, these are three special angles, and you'll see that in the next concept talk I'm going to be making use of these three angles to come up with a nice nifty relationship. But here are the three angles. Okay, I'm going to mark them first from the tail of the vector F all the way to the z-axis, then from the tail of vector F all the way to the y-axis, and then from the tail of f all the way to the x-axis. Okay, so these are three angles, and I'm going to call them as gamma, then beta, and then alpha. Okay, and these angles are called as the coordinate direction angles. So I'm going to write them here. Okay, so the angles alpha, okay, is the angle made by the tail of vector f with the positive x axis. That is very important. Then the angle beta is the angle made by the tail of the vector f with the positive y axis, and the angle gamma is the angle made by the tail of f with the positive z axis. And these angles alpha, beta, and gamma, okay, so this is the first thing. These angles alpha, beta, and then gamma, these are called as the coordinate direction angles. Okay, one thing you want to realize is that these angles are on different planes, which I'm going to be drawing in our next concept talk. Okay, these angles are on different planes. The angles are all on different planes. Okay, so see my next short lecture. And it is not necessary, and it is most definitely not going to be the case, that alpha plus beta plus gamma is not equal to 360 degrees. Okay, this is not a relationship that is valid, because these angles are on different planes. Okay, because alpha, beta, and gamma are on different planes. All right, so these are the things about the coordinate direction angle. So quick things that we have done here. I just want to underline a couple of important terms. So coordinate direction angles. Okay, the most important thing is the angle made by the tail of the vector f with the positive directions. Okay, likewise, tail of vector f, always the tail with the positive directions. Always the tail with the positive directions. Okay, these are the angles alpha, beta, and gamma. All right, I hope all of you are staying safe. I'll be seeing you in my next concept talk. Thank you.